Well, in this problem, it is really a typical two-body problem, but this is about the application of Newton's first law, as the whole system in here is in a static equilibrium, and it's required here to find the weight of the block A. Well, it's given the weight of the block B, where you can find the mass easily from there. And also there is a friction between the block B and the table, and this friction is a static friction. To solve this problem, you have to draw three body diagrams instead of two. That's one for B, one for A, and one that at the node, at the junction of the three ropes. Obviously for B you have the weight downward, that's MBG, and you have also a normal force upward for this, a normal force Fn along the y-axis. Obviously along the y-axis there is an equilibrium as well, and the sum of forces along the y-axis should be zero. Along the x-axis there is a tension in the rope, because this weight will put tension on the other two ropes, and this one has a tension in this direction, call it T1 if you like, and there is a static force of friction where the is supposed to be in the verge of slipping at this guy, Fs maximum here. That's why when we said this is Fs maximum, that's why the weight here is considered as a maximum weight, because we need to overcome the maximum static force of friction in order to get this on the verge of slipping, while the mass A is going to be responsible for pulling the whole system on the verge of slipping. Now this is the whole forces on B. The forces on A, obviously when you have MAG in this direction, you will have a tension here, we'll call it T3 if you like, T3, and then you have a tension also as long as this rope is attached to the wall, you have a tension of T2. Then what you have actually here, you'll get an equation from this, from the block A, as T3 equals MAG, and you have two equations for the node, one along the x-axis, that is T2 cosine 30 minus T1, and this direction is going to be this one, for along the x-axis equals 0. And we should remember here, we forgot this point, at the knob also we have a component for T2, that's T2 cosine theta, cosine 30. This must be in equilibrium with T3 downward in this direction, T3 as well. Again, you have one equation along y-axis for A. You have two equations, one for the knot, one along the x-axis and the other along the y-axis. And we have also two equations, one for the x-axis and one for the y-axis for B, but we don't need too much that one for B, for along the y-axis. We are interested for that one along the x-axis. Now, by solving all these equations, you can you will end up, this is 4 equations, and we have 4 unknowns. That's T1, T2, T3, and MAG. will be able to solve them and get MA from this problem. And the answer is going to be 103 Newton for A. This is an interesting exercise for the student to do. It's really a challenge problem. And here we have two blocks connected by a massless string and are moving along an incline of 30 degrees. The lighter object of 3.6 Newton, the yellow one, that's A, block A, and the blue block with a weight of 7.2 newtons. And here it's considered that the two blocks of different materials, given the coefficient of kinetic friction between the lighter block, that's A, and the incline as 0.1, while the coefficient of friction, of kinetic friction, between the block B with different material and the surface as 0.2. Now, how can you get the magnitude of the acceleration of the two blocks and the tension in the strings between them? And you are asked to describe the motion if instead the heavier block leads, because here in this problem it's assumed that the lighter block is going to lead the system. Again, to solve this problem, you have to cite the forces acting on each block and draw the free body diagram. And the forces in here is the weight of the block A, and obviously this weight will have a component along this direction, because the angle between the weight and the normal, this is the weight, and the normal surface is the normal. This angle is the same as the angle of the incline, as we said before. And you have these forces, and then expected here a tension in this direction, because as this one will try to draw this one will oppose the motion, and the tension becomes for A in this direction. And there is a tension T in here. So here we've got an equation along the x-axis, which is going to be in the direction, this is the positive direction of the x-axis, will be considered as positive. As the motion, the whole motion, we're going to consider it as positive in this direction. So in this case, you set up the equation, Newton's second law for this one, where there is a force of friction that is F Ka, and obviously if Ka, we should not forget that it has a 0.1 value for coefficient of kinetic friction. While here we have a component of the weight mg sine theta along this direction, and there is a tension in the rope along this direction as well. While here there is an opposing force of friction, that's Fkb, which is different from that one of A, because here we have 0.2 more coefficient of friction, and we have a different orthonormal force, because the mass of B is different from that of A. And in addition, here we have obviously MBG, where it has two components, one along the axis here, which is, as I said before, and there is one here opposite to the normal force. By solving this equation, you're going to get the magnitude of acceleration and the tension, And then when you consider the assumption of the heavier block, you have to see what's going to happen. And here is the answer for the acceleration, and 3.5 meters per second for part A of the problem, and for part B of the problem the tension is 0.2 Newton. This is an interesting exercise. Here we have a block weighing 22 newtons, obviously downward, 22 newtons, and is held against this vertical wall by a force of 60 newton. And it's given the coefficient of static friction between the block and the wall, and also the coefficient of kinetic friction is also given. A second force, B, is acting parallel to the wall, is applied to the block. For the following magnitude and direction of B, you have to determine whether the block moves, the direction of its motion if it moves, and the magnitude and direction of the frictional force on the block. In part A, it's given that 34 newtons up for B, if it is up like that. For part B, for part A, the expected answer block does not move. So you should solve the problem and decide why it does not move. For the second part in B, 12 newtons up. So the first part 34 newtons up, the second part 12 newtons up. Then again it says the answer, the block does not move. So you have to tell us why the block does not move. And part C, 48 newtons up. Also it says in part C the answer, block does not move. With a 62 newtons up, it says here in part D that the acceleration, there is an acceleration, and that acceleration is 7.6 meters per second square up. So you should give us an answer why the answer is expected to be like this by solving the problem. And then in part D, if we have 10 newtons down, the block does not move. And finally, in part F, we have 18 newton down, and the acceleration is 7.6 down. So in each case, you should give us the way and to get the solution and convince us with the answer. This is another challenging problem where, as shown in the diagram, we have two blocks A and B attached by a rope, by a massless rope, and passing over a frictionless pulley, also massless pulley as well. And the weights of the two pulleys, 44 newtons for A and 22 newtons for B. And then there is a friction between block A and the table, and it's given the static force of friction, the coefficient of static force of friction as 0.2. And it's another block C is placed over block A. And in this case, the system is in equilibrium, and you are asked to find the weight of block C that keeps block A from sliding. It means to keep the whole system in equilibrium. And part B, if this block C is suddenly removed, then the system will accelerate. And what is the acceleration of the system if the coefficient of kinetic friction is given as 0.15? Obviously, the student should be very careful here when drawing the free body diagrams, because we have here three bodies, and in the first case, the static force of to find the weight of the block, we have to consider here there is MAG, this is the weight of G, and here we have MAC as well, the weight MCG, the weight of the block C, and we have a normal force for C, FNC, and also we have here a normal force for an A. So in doing the first part, you should consider all these forces. For part B, for block B, you have MBG, the weight MBG, that's the weight of the block, and then you have a tension, and obviously here you have a tension as well, and you have a static force of friction, Fs maximum, and the minimum weight to keep this force of static friction, the verge of slipping, is that of MC, we want to find in this problem. Then by setting the free body diagrams, you're going to get an answer for the mass or the weight of the block C. In part B, when you move this, you should consider now a kinetic force of friction instead of static force of friction, and you have to take into consideration that the Fn for the block A, to get it from the new equation, and then you'll find your final answer for the acceleration. And the given values for part A for the weight of C is 66 Newton, and for the acceleration of part B, 2.28 meter per second square. This example is all about the difference between the true weight and the apparent weight, and we're going to see that this gentleman is in an elevator and having a spring scale where he can weigh himself in each single of time, while the lift or the elevator is going up or is accelerating or decelerating. And here the apparent weight, where the spring scale reads a reading of 591 newtons when the elevator is start moving with an acceleration upward, and then when it starts to decelerate in order to stop at the end, so it's going to decelerate, and it has a weight of 391 newtons. Here, if you assume that the magnitude of the acceleration is the same during the starting and stopping stages, you need to determine the weight of the person, means the true weight and the person's mass, and the acceleration of the elevator. For the first part of the problem, we have the reading of spring scale, which is the apparent weight as 591 newtons, and the acceleration is positive upward, so you have the resultant acceleration of the person is m times a, and the forces acting on the person is a spring scale, which is upward, and the weight is downward. If you put in the values given, we get equation 1. For the second part of the problem, if the elevator starts to decelerate, I mean it's about to stop, means the acceleration is negative in this case, then we have the apparent weight of 391 newtons, and again the resultant is of the person is m times a, where the acceleration here in this case negative as given in the problem, while the reading of the spring scale is up and the weight is downward. So we will have another equation by inserting the given values in equation 2. By solving equation 2 and 1, you might be able to get a mass for the person with 50 kilogram and the weight of 491 newtons, and this is the true weight of the person, while a value of acceleration also can be obtained of 2 meters per second square. Again, do you learn anything about Newton's first law? Well, I'm waiting for the answer.